In order to understand and apply the fundamental theorem, you first need to learn about antiderivatives. The antiderivative of a function f of x is another function, capital F, such that the derivative of capital F is f itself. If taking a derivative means that you go down in the hierarchy of functions, then taking the antiderivative means going up. Let's look at some examples, and let's start with the simplest possible quadratic function f of x equals x squared. You know what you will get if you take the derivative, right? Of course, the derivative is 2x. The rule was that you take the exponent, drag it to the front, and as a payment for this, reduce the exponent by 1. In order to get the antiderivative, we have to do the exact opposite. We increase the exponent by 1, and then we drag the inverse of this new exponent to the front. If you want to check your result, you just need to take the derivative. Well, it works. If we take the derivative of the antiderivative with the y, we needed to drag the inverse to the front. The 1/3 compensates for the 3, which you would get if you would take the derivative of x to the power of 3. Here's another example. Stop the video here and compute f prime and capital F. Really, do it. We need to read the -2 as -2 times x to the power of 0. Then we can increase the exponent by 1. And if we have a coefficient in front of the power, like here, then we just divide it by the new exponent 5. So what is the general rule? Stop the video again and fill in the results yourself. Note that a is not necessarily a natural number. A can be fractional or even negative. We will call this rule the power rule. Here's another example. As you know, the square root can be written as x to the power 1/2. If we use the power rule, then we get this, which we can rewrite with roots and fractions in this fashion. Recall that negative exponents transform into fractions. If you don't remember these things too well, please look them up. Try to find the antiderivative of the root function yourself. So again, it's the opposite of taking the derivative. There you first drag, then decrease. Here you first increase, then drag, and you drag the inverse of the exponent. Here's a last example, 1/x squared. It can be written as a power with the exponent -2. So again, you can use a power rule and then retranslate to fractions. Stop the video and try this, please. Well, if you subtract 1 from -2, you get -3. And if you add 1 to -2, you get -1. And don't forget these minus signs. By now we can compute the antiderivative of some functions, but what is the meaning of this antiderivative? Let's look at this parabola. You know what it means to take the derivative at a point, say at 2, 0, don't you? You get a number, and this number is the slope of the graph at this point. Instead of drawing a tangent line, You might as well draw a little line segment, a dash, which has the right slope. Well, and the derivative function gives you this information for all values of x. You feed in any x into f prime, and out comes the slope for f for this x value. Now, what if our function, small f, already contains this information for the function capital F we are after? Then we know, for instance, that for x equals 2, the slope of capital F must be 0, because f of 2 equals 0. So at x, there must be a minimum or a maximum or a saddle point. So why do we draw the horizontal dashes on top of each other? Well, let's get busy and draw some more of them. We know that capital F must have a horizontal tangent line at x equals 2. What we do not know its y value. It could be anywhere on this parallel to the y-axis. If you draw lots of these directions, you get an idea how the shape of this antiderivative must look like, but how do we get it? We need to make a choice. We choose to start at some point on the y-axis, say at 0, 1. You may imagine that this red point is a robot which starts marching forward in positive x direction. The robot is programmed to march in exactly the direction of the point he's standing on. See what happens. It could have marched backwards as well. So what is the term of this antiderivative? We take the antiderivative of each term as before, but in the end we have to add a 1 because we want f of 0 to be 1. That was our choice at the beginning. Which begs the question, why did we choose 1? We could have started on any other point on the y-axis, like on 0, 2. And indeed, this gives another antiderivative. Term looks almost exactly like the one here, but there's a 2 at the end, not a 1. Or you start at 0, 2.5, or at 0 minus 1, so actually there's not just one, but there are infinitely many antiderivatives. But they are all parallel because for a given x, they have all the same direction. This is what defines them. So once you find one antiderivative, you can just get all the others by simply adding a constant c at the term of the one you found. Finally, some words about notation. You probably know that you can write the derivative of f not just by adding a prime on top, but also by putting a ddx in front. Physicists like to do this, and it should remind you that what you're doing when deriving a function is computing difference quotients and going to the limit. Similarly, you can write an antiderivative by switching from a small letter to a capital letter, as we've done, or by writing it as an indefinite integral. It looks like an integral, but the limits at the bottom and the top are missing. So it is no longer a definite integral, but an indefinite integral. The power rule, which we used at the beginning, can be written by means of indefinite integrals. Note that we cannot use this rule if a is minus 1, because then both the exponent and the denominator of the fraction here would be 0, and we can't have that. The antiderivative of x to the minus 1 will turn out to be the natural logarithm, but this is something to look forward to next year. You may wonder, where's the connection between integrals and antiderivatives? After all, integrals are numbers and antiderivatives are functions. It will turn out that this notation already encapsulates the gist of the fundamental theorem, which will be the topic of the next video. Thank you for watching.